This is it! This is the lecture you've been waiting all semester for, even though you didn't know it. In this lecture, we're going to learn how to take any circuit, no matter how complicated it is, and simplify it down to its simplest form. Yeah, that's right, you're going to be able to do that. You're going to be able to take a circuit and make it so simple that even if you had Elon Musk, Albert Einstein, and Claude Shannon on the same dream team trying to make it simpler, they could not make it simpler than you. I'm going to teach you that today. I gotta be honest. This is a hard lecture for me to do. You see this 2 here? That's because I already recorded this entire lecture once before. It took like 3 or 4 hours, and then I played it on YouTube, and I realized that like half the lecture was cut off in the video. Like you couldn't see the whole top half of the screen. So, you can make it through this one because I've done it twice now. Alright, so let's talk about Karnaugh maps. Like I said, they're so great because you can take any circuit, simplify it so that it can't be simplified anymore. Right? When you were doing that Boolean substitution, sometimes you weren't sure, is this as small as it can go, or maybe we could have done better if we went some other way. So that's one of the reasons K-maps are so good. The other reason they're so important is if you know what the inputs and the outputs need to be, which you pretty much always do if you're designing a circuit. So if you can make a truth table for it, you can design any circuit from scratch. You don't even have to know how AND gates and OR gates work. Following this process, you'll be able to design any circuit that you can dream up. So that's why K-maps are so important. It is unequivocally the most important lecture this entire semester. So, of course, that's the one I messed up. It's going to be the most important lecture for all of your classes going forward. Every digital class you take from now on will involve K-maps. So I think that's enough build-up, right? Let's go ahead and get started. So, the good news is, a K-map essentially is just a truth table drawn a little bit differently. And we're going to look at that now. You can still see my old marks from before. So, this is a truth table. Hopefully it looks pretty familiar to you. It's called 2 variables because notice it has 2 inputs. Right? So remember we have our inputs over here on the left, and we have our outputs over here on the right. What a truth table tells us is no matter what the 2 inputs values are, it gives us what the output should be. So as an example, if A is 0 and B is 0, the output X should be 0. Down here, if it's 0, 1, it should be 0. If it's 1, 0, it should be 1. And if it's 1, 1, it should be 0. So, let's see how we turn this into a K-map. For a 2-variable K-map, what you want to do is you want to draw a square. So I'm going to draw a square. Just like this. And then you want to cut it in half twice. Once vertically, and once horizontally. Just like this. And so remember, it needs to have 4 cells. Because just the same as the truth table has 4 rows, if I have 2 inputs, remember it's always 2 to the n, I need 4 cells. Outside of that, we draw a little line here, and we say that A is represented on the vertical axis, and B is on the horizontal axis. I put a 0, I put a 1, I put a 0, and a 1. And then we fill it out just like the truth table. Before I do that, let me make sure everybody understands this. This row is for all of the values of A that are 0. This row is for A where it equals 1. Same thing over here. This column is where B equals 0, and this column is where B equals 1. So this first cell represents 0, 0. And again, it's just because we've got 0 on the horizontal and 0 on the vertical. Can you guess what this one would be? I hate teaching online, I wish I could hear you, but hopefully you said 0, 1. This one down here, 1, 0, and this one would be 1, 1. So let me erase all my extra marks here. Now notice that these boxes correspond to those rows of the truth table. And so to fill this out, all we have to do is we have to put a 1 wherever there's a 1 in the truth table. For K-maps, we don't write the 0. If it's blank, we assume it's 0. And so notice in this truth table over here, the only place that's a 1 is at 1, 0. So I need to go to 1, 0, and put a 1. That's it. That's all there is to it. Well, that's not all there is to it. We're going to learn how to solve it and use it to simplify in just a few minutes. But first, I want to make sure you know how to draw it and you know how to fill it out. Any questions? Yeah, right. Okay, moving on. Let's look at a 3-variable one. Again, it's 3 variables because notice we have 3 inputs over here on the left. Because we have 3 inputs, that means this truth table or this K-map needs to have 8 entries. So here's how we do it for an 8-entry one. We first want to draw a vertical rectangle. I want to cut it vertically once, and I want to cut it in half 3 times horizontally. Did I say that right? Sounds backwards. Okay, so now notice that we have 8 squares. On the left, we're going to represent both A and B, and vertically, we're going to represent C. Now here's probably the trickiest part of getting K-maps right. And I'm also going to explain why K-maps work. When we go to number this, we have to number this 0, 0, 0, 1. So far, everything's going good. Here's the tricky part. We next need to go to 1, 1. And I'll explain why that is in just 1 second. So 0, 0, 0, 1, 1, 1, 1, 0. And across the top, 0, 1. Let's do that same thing where we say what the values are. So notice this would be 0, 0, and 0. This would be 0, 0 from the row and 1 from the column. This would be 0, 1 from the row and 0 from the column. This would be 0, 1, 1 from the column. 1, 1, 0. 1, 1, 1. This would be 1, 0, 0. And this would be 1, 0, 1. Make sense? This is a good time to explain why K-maps work. You don't need to know what I'm about to tell you. If you just want to remember, I always write it this way, remember you always write it that way. But here's the reason that we draw the K-map different. If you notice, when I go from this number to this number in a truth table, 2 bits change, right? This 1 gets turned into a 0, this 0 gets turned into a 1. The way that a K-map is different is if you notice going from one box to any other box, only 1 bit changes. So with the one I just drew, the first one goes from a 0 to a 1, but the others stay the same. Notice from this one to this one. The last 1 becomes a 0, but all the other bits stay the same. Same thing if I go this way. Notice that the middle one goes from 1 to 0, but the others stay the same. It even works if I go all the way from the bottom, all the way to the top. Notice we go from 0, 0, 1 to 1, 0, 1. So only bit flips. Only 1 bit flips. That's really important for what we're going to do in just a minute. It's going to allow us to simplify any circuit. So that's why we number it different, and that's why the K-map is so powerful. So let's go ahead and try to fill this K-map out for the numbers that we have on the left, for the truth table we have on the left. Erase this, erase this. Okay, so remember, we don't need to write the zeros. The first one I need to write is this row right here. So we have 0, 1, 0. So I go to the 0, 1 row, and I go to the 0 column, and we put a 1 at 0, 1, 0. Next, we have 1 at 0, 1, 1. So again, I go to the 0, 1 row, I go to the 1 column, and I put a 1 there. These are zeros, so we don't need to write them. I come here, and at 1, 1, 0, we have 1. So I go to the 1, 1 row, and the 0 column, and I go to the 1, 1 row, and the 1 column. And that's it. That's how you fill it out. Still with me? Alright, let's try it as complicated as I'm going to make it in this class. Let's try a 4-variable one. Okay, so for 4 variables, we have 4 inputs, right? So if I have 4 inputs, that means we're going to need 16 cells, just like we have 16 rows over here. So here's how we draw this one. Again, we go back to making just a perfect square, or as perfect as you can draw. this is not that perfect. We're going to cut both vertically and horizontally 3 times. There's my vertical. Why does everything slant up when I draw? And there's my vertical. I said it backwards again, didn't I? Over here, AB, and over here, CD. Okay, when we number it, good news is we do it exactly the same. So we have 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. And again, our same rules apply. If you go from this box, I'm not going to do them all because I don't want to take your time. But if I go from 0, 1, 1, 0, notice over to here to 0, 1, 0, 0, still only 1 bit flips. If I go from here, 0, 0, 1, 0, only 1 bit flips. If I go down here, 1, 0, 1, 0, only 1 bit flips. So again, that's why this is drawn with that funny numbering system. Let's try filling it out. So we don't need to write the zeros. I start here at my first one, and I have 0, 1, 0, 0. So notice this is AB, so I go to 0, 1, and 0, 0, and I put a 1. Next up, 0, 1, 0, 1, which is this one, so we put 1. Next up, we have 0, 1, 1, 0, so 0, 1, 1, 0, that's this one. And then finally, we have 0, 1, 1, 1. So 0, 1, 1, 1, I put a 1. Alright, that's those. Let's go down to this one. 1, 1, 0, 0. So 1, 1, 0, 0 would be this one. We have 1, 1, 0, 1. So 1, 1, 0, 1 would be this one. Next up, 1, 1, 1, 0. This is 1, 0. So we have this one. And finally, we have all 4 ones. 1, 1, 1, 1. So that would be this row with this column, which means right here. And that's it. That's all there is to the first part. Told you it wasn't so bad, right? It's not too hard. What happens if I have something like this? So now we're going to see why I made you do all of last week's lecture. Why did we need to know that sum of products thing, that standard sum of products thing? Well, let's start. First of all, is this sum of products? And again, the reason we're doing this is, let's say that we came up with some design, we wrote down the equation for that logic design, we want to know, is this as simple as it could be? We could try doing the Boolean substitution, but even if we did it, we wouldn't be sure at the end if it could have been simpler if we would have gone a different direction. So this is how K-maps work. First question, sum of products? Yeah, it is, right? Notice that it's a whole bunch of products, product meaning and or multiplication, all connected by one OR gate. Alright, is it in standard form? And it turns out it is, right? There are 3 variables here, A, B, C. All terms have A, B, and C in it. And so yes, this is in standard form. So all we need to do is figure out where is this thing true. Remember, these are a bunch of OR gates. So as long as any one of these ANDs is true, the whole thing is going to be true. And so I just have to figure out where are those AND gates true. Well, this AND gate will be true if A is 0, B is 0, and C is 0, because it'll invert it and turn them all to 1s. It'll be true if 0, 0, 1 is our input. It'll be true if our input is 1, 1, 0. And then finally, it'll be true if it's 1, 0, 0. In case I went through too quickly there, notice all I'm saying is if it's just the letter by itself, that needs to be a 1. And if the letter has an invert over it, it needs to be 0 so that it becomes 1. Alright, so what size K-map do we need here? Well, we've got 3 variables, which tells me we need 8 cells. So remember, that's the vertical one. The vertical rectangle thingy. That's a technical term. Vertical rectangle thingy. Cut it in half. Cut it in half. Cut it in half. Cut it in half. Boom. Remember, upper left is AB. Over here is C. By the way, your variables might not always be A, B, and C. Right? This could have been X naught, Y naught, C naught. If that were the case, then this over here would just be XY, and I kept C. This would be C here. So it doesn't matter. Just make sure you have it in the right order. The order matters. What the letters are named doesn't matter at all. So again, don't forget when we number this, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. So our first one is 0, 0, 0. So I go to 0, 0, 0. We put a 1 here. Next we have 0, 0, 1. So that's the same row, but this column. So I put 1 here. Next we have 1, 1, 0. So that's here and here. So here. And finally we have 1, 0, 0. So 1, 0 row and the 0 column. That's it. Alright, let's crank it up a notch. What if I had this one here? What do you think? Well, what's the first step? Actually, the first step is De Morgan. Do we need to De Morgan this? No, I don't think so, right? We have overbars, but they are all over only one letter. So that looks good. Step 2. Do we need to distribute, multiply it all out? No, it's already in sum of products form. Is it in standard form? Yeah, I think it is, right? We have 4 variables. Each of them is included in all of the products. And so we're good to go. All we need to do is label where is this thing true. Remember, that's the whole reason we're doing this, is to find out where it's true. Well, it's true at 0, 0, 1, 1, at 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 1, and at 1, 0, 1, 0. Alright, what's our K-map look like? It is a big square. It has 16 cells. We'll draw it out. Big square, cut it in half both ways 3 times. That's one way. That's the other way. In a little bit, I drew one out, and I just copied and pasted it and made it nicer, so you won't have to look at my blue drawings forever. AB, CD, 0, 0, 0, 1. What comes next? Yep, 1, 1, 1, 0. For any of you who are interested in a technical term, that's actually called gray code. Type of thing. Gray code. We used to use it a lot back before we had smart sensors for, like, detecting. Well, I say we. I'm not that old, right? When I say we used to use it, I mean the people who came before me, too. But anyway, you get the idea. It's called gray code. That's all that's important. No, it's not really important, but that's all I was trying to say. Alright, fill it out. Alright, so 0, 0, 1, 1. 0, 0, 1, 1. Boom. Next up, 0, 1, 0, 0. 0, 1, 0, 0. Next up, 1, 1, 0, 1. 1, 1, 0, 1. 1, 1, 1, 1, 1. 4 ones. That's here. 1, 1, 0, 0. That's here. 0, 0, 0, 1. 0, 0, 0, 1. And 1, 0, 1, 0. 1, 0, 1, 0. That's it. Next. How about this one? Do we need a De Morgan? No. Is it in sum of products? Yes. Is it in standard sum of products? No. Fail, right? Notice that our first term is missing B and it's missing C. Our second term is missing C. And so do you remember from last week what we need to do here? Well, the first term is missing 2 values, which means there's 4 possible values that we don't have written here. For all 4, for this to be true, A has to be 0. But notice, for these missing ones, if B and C were 0, this would still be true, right? All it cares about is A naught. If it were 0, 1, that'd still be true. If it were 1, 0, that'd still be true. And if it were 1, 1, it would still be true. So that's why we're doing this. We're basically saying as long as A naught is 0, this whole equation is going to be 1. And so we have to include all the values of B and C. Here we're missing 1. which means there's two possibilities. C could be 0 or it could be 1. Over here, that's the only one that's going to make that true. So again, we've got 3 variables. So we draw a 3-input K-map. Long rectangle, cut in half 3 times along the vertical and once on the horizontal. We've got A, B, we've got C, 0, 0, 0, 1, 1, 1, 1, 0, 0, and 1. And we just fill it out. 0, 0, 0, boom. 0, 0, 1, boom. I'm going to go through these quicker now. If you're having trouble with it, go back and look at it again. Where I went slowly. I think you got it by now, right? I hope. If not, and you don't get it from the video, just contact me. 101 and 110. There we go. And the last one before we start more stuff, different stuff. De Morgan's, done. Sum of products, done. Standard sum of products, not so much. Right, we got 4 variables here. This one's missing A. This one's missing D. No, the same one. It's missing A and D. We're missing B and D. And the last one has everything. So again, if we are missing 2 variables, there are 4 combinations we're missing. For all 4, 0, B and C have to be zeros. This could be 0, 0, it could be 0, 1, it could be 1, 0, or it could be 1, 1. In this case, we're missing 2 again, so there's 4 rows that we're missing. For all 4, A has to be 1, and C has to be 0. And then, did you guys watch the homework video where I showed you the shortcut for filling out truth tables? If you watched that, homework solution, I give you a way to fill out truth tables really, really quick. Or count really, really quick. Alright, so we've got all of the places that it could be 1. All we need to do now, draw out our 4 variable K-map. So again, that's a square, cut in half 3 times each side. Alright, A, B, C, D, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. And we fill it out. So 4 zeros, that's here. 0, 0, 0, 1, so 0, 0, 0, 1 is here. 1, 0, that's bottom row. 0, 0, that's here. 1, 0, 0, 1, 1, 0, 0, 1 is here. 1, 0, 0, 0. Notice we already got this one. That's right here and it's already filled out. That's perfectly okay. We don't need to write it twice or anything. Just basically ignore it. What is that? Where did that come from? It won't go away. I have no idea what that is. Can you guys see that? Anyway. Uh-oh. Yeah, 1. 1, 0, 0, 1 is already filled out, so we don't need to do it again. 1, 1, 0, 0 is here. 1, 1, 0, 1 is here. And 0, 0, 0, 1. 0, 0, 0, 1. Already filled out. Look at that. So I can tell you one thing, this circuit is going to shrink a lot. Yep. We're going to be able to turn it into 2 terms of 2. We're getting to that. Alright, so I need you to know how to do this. Everything that's coming up is going to completely confuse you if you can't do this. So I'm serious now. Stop the video. Stop it. Pause it. Try to do these 3 on your own. Make sure you can do these 3. If you can't do these 3, go back and watch the first part again. Alright, I'm going to show you the answers. They're coming in just a second. Okay, so you solved them, right? Here are your solutions. Yeah, look at those rectangles and squares. They're drawn better, aren't they? Did you get it? If you got it, great. Stick with me. If you didn't, go back and watch that section again. You really gotta know how to do this. Alright. So now, how do we actually use these K-maps? You didn't think this was all we were gonna cover, did you? No, we have to use them. And here comes the part that you don't want to see. I promise it's not that bad. These are the rules. We're gonna go through it step by step. And I'm gonna confuse you a whole bunch. And then we're gonna try some. And you're gonna see it's not that bad. So, step 1. is you need to transform whatever equation, whatever circuit you have into a standard SOP to get all of the ones. Okay, step 2, we got to fill in the appropriate K-map. So that's what we've been practicing, for the last half hour or so. All right, here's the new stuff. We need to group all of the ones. So, K-maps kind of look like this, and you get a bunch of stuff like this, and a bunch of stuff like this, and you get a bunch of ones like that. We have to group them. So, here's how we have to group them. We have to follow these rules. Groups must contain a power of 2 number of cells. What this means is I can have a group with just 1, I can have a group with 2 ones, I can have a group with 4 ones, but I can't have a group with just 3 ones. That can't happen. So all of our groups must have a certain number of ones that is a power of 2. Next up, this isn't Tetris. All of our groups have to be perfect squares or rectangles. So, we can't have a group that looks like, I can't even draw a Tetris. Can't have a group that looks like that. It's got to look like this, or it's got to look like this. The groups must be as large as possible. Okay, so if I have a choice between a couple groups, I have to make the group as big as it can possibly be. And we'll see what this means in just a second. Don't worry about it too much now. Wrap around okay, meaning we can go from one side to the other. By the end, every single one must be included in some group, and it's actually okay if a 1 is in more than one group. And using those groups, we're going to be able to determine what the simplest possible equation is. So you're really confused now, right? That's kind of the goal, going through these by themselves with no, in the abstract. I know you're confused. It's not that bad. Let's take some examples. So what I want to do right away, hold on one second because I forgot to do something. Boom! There we go, movie magic. Alright, so what we need to do is we need to group these ones, and we got to remember to follow our rules. So the first rule is we need to make the group as big as possible. So notice, I probably don't want to start with this one up here that's all by itself because I can't make a very big group there. Always try to make the biggest group first. So to me, and I'm going to do these in different colors. You don't need to do it in different colors. I'm doing that so when I show you something later it makes sense. So the first group I see is this one right here. Right? There's a group of 2. Remember, we can't make this like this with a group of 3 because groups have to be powers of 2 and they can't be irregular shapes. Alright, the next group that I see is I can do a group like this. And notice, I could have just grouped this one by itself, but it's better to make it bigger. We need to make it bigger. So even though that other one is now in 2 groups, that's okay. It's better to have it bigger. Why won't that come back? There. It's better to have it included in 2 groups if it makes one of the groups bigger. And remember our last rule. Everyone has to be in a group, even if it's all by itself, like this guy up here. There we go. So now all of our ones are in groups. So that's it for grouping. Now we have to go to the part where we make an equation for it. And this is the part that's going to be at first a little bit confusing. So before I go straight there, I'm going to show you over here what we're going to do. So notice in this area, this A is this. Right, these are our values for A for all of these boxes here. So for instance, A is always 1 in this box, always 1 in this box, always 0, and 0 in this box. And so what we're going to do using that, I keep erasing my stuff. What we're going to do is this. I'm going to say that this here is the A region. It's the A region because notice A is always 1 in these rows. So A is always 1 here. It's always 1 here. It's always 1 here. And it's always 1 here for all of those 4 boxes. So that is the A region. Those 4 boxes are the A region. Notice that B is always 1 for these 2 rows. Right? B will always be a 1 here, 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 and here. So far so good? C is this column here. because C is always 1 in these boxes. And so that's what we mean by these regions. That's the A region because for all 4 of the boxes, A is 1. This is the B region because for all 4 of those boxes, B is 1. And the right column is the C region because for all 4 of those boxes, C is 1. So now let's go back to our example. As I said, this is the A region. This here, these 2 rows are the B region. And this is the C region. Now what we need to do is go to each of our groups one by one. So I'm going to start, I'm going to use the same color of the group I'm looking at. So I'm looking at the blue group now. I think it's blue. Could be purple. I don't know. I'm colorblind. But you know what it is, right? The one that's not red or white. Alright, so we're at that group. Notice, is that group entirely, so all of it inside of A? Is all of it outside of A? It's neither, right? Notice that this box here is outside of the A region. 'Cause remember, these bottom 4 down here, right? These 4 are the A region. Notice this one is inside, this one is outside. And so what that means is we can't draw any conclusions. We don't write down anything. Now we go to B. Is this group entirely inside of B or entirely outside of B? Well, notice both this box and this box are inside of B. Since they're both inside of B, we write B down. Next, is it entirely inside of C or outside of C? Well, both boxes are in the C range, so we write C. And what that means is for that group, B always has to be 1 and C always has to be 1. After that, we write an OR gate. Now we're going to go to the next group. So I usually start big and work small. So I'm going to look at the red group now. Is it entirely inside of A? The answer is yes. All of this group, so both of these boxes are inside of A. So I write A down. Is it inside of B? Yeah. Both this box and this box are in the B region, which we've drawn in blue on the right. And so I write B down. Is it inside of C? No. This one is in C, but this one is not in C, so we don't write C. Next, let's look at the white one. So this box up here, notice that it's entirely outside of A. If something's entirely outside of A, we write A naught. Notice it's entirely outside of B as well. No part of it is in the B region, so we write B naught. Same thing for C. The entire box, all of this group, is outside of C, so we write C naught. And that's it. That is the simplest this equation could ever be. And that's all you have to do to solve these problems. So if I have a truth table, I can put it into a K-map, and I immediately know the circuit that I have to build. In this case, right, I would need B, C going to an AND gate. I would need A and B going to an AND gate. And I would need A with an inverter, B with an inverter, running out of space here, and C with an inverter going to an AND gate. And boom, we built our circuit. Alright, let's try another one. What is the biggest group you think we can make? I'll give you a second. How many of you guys said a group of 2? It's true, we could do a group of 2, but I think we can go bigger. What about this? Notice if I group these 2 with these 2. Ah, you think I'm tricking you, right? Remember, I said you gotta kind of think of this as a sphere. This is next to this is next to this, and so on. And so wraparound is okay. Those 2 at the top are connected to the 2 at the bottom. Next, again, we don't want to do this, right? It's better, it's better if we make it bigger, even if it means grouping it with another one. So that's our second group. And finally, this here is our third group. So now we just need to write the equation. Again, remember this is A, this is B, and this is C. So I'm going to start with the blue group. Notice that it's half in, so these here are inside of A. These 2 boxes are inside of A. but these two boxes up here are outside of A for that group. So I would write A9. Notice, oh, what am I saying? I would not write A9. Bad code. I wouldn't write anything because it's half in and half out. Let's look at B. Notice that both of these boxes are outside of the B range. Remember, this is B over here, the middle two rows. And so I would write B9. It's half in, so the two on the right side are inside of C, but the two on the left side are outside of C. So we don't write C, we don't write anything. Now let's look at the red group. Alright, notice that both of these boxes, this whole box, is inside of the A range. Notice that this box here is inside of B, but this part of it is outside of B, so we don't write B. It's half in, half out. And finally, both of these boxes, this whole group is inside of C, so we write C. Finally, our last one, up here. Notice that both of these boxes are outside of A, so we write A0. Notice that this one is in B, but this one is outside of B, so we don't write anything for B. And notice that they're both outside of the C range, so we write C0. And that is it. That's the smallest that circuit could ever be. And by the way, you can see on this, right? The bigger the group, the less terms we need. That's why it's always better to make it bigger. Alright, let's do the same thing for this one. So notice, let's do the regions first. So notice, just like before, the bottom two rows are where A is 1. So A is 1 here, 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 and here. Just like, so this is the A region. Just like before, let me pick a different color. This here is the B region, because notice that B is 1 for both of those two rows. So we have B, 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 B equals 1, B equals 1, and B equals 1. Alright, kind of like before. Let's see, and then a new color. What's a good color? I don't have that many. This region up here is the C region. Kind of just like before. Notice C is a 1 and C is a 1. So this, 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 this. Does this color thing working for you? Does it help? I don't know. I've never taught it this way before. I've never had color. That's the C region. And I think I'm really out of color. Oh wait, I forgot red. How did I forget red? There we go. I can't see red. Maybe that's why I forgot red. And then notice that this one here is D, and so the middle region is the D region. And so that would be here. Both of these two middle columns. La 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 la. There's my masterful artwork. And so those are the regions. I hope that helps. Looks like a mess now that it's all done. Alright, so let's do it. So again, let me write my regions. A, B, C, D. Okay, so we have to group this. Like I said, to make it easier on yourself, always group the biggest group first. And the biggest group I see is this one right here. Group of 4. Remember, it's a power 2. It's a perfect square rectangle. That works. What else do you see? Well, next biggest group I see looks like these two by themselves. Doesn't seem to be much we can do with them. And then finally, again, we don't want to just do a group of 1. It's much better to do a group with both of those. So now it's time to write our equation. We'll start with the blue box first. So notice it's outside of A, because all 4 of these are outside of the A range. It's inside of B, And notice that it crosses C and D. These two are in C, these two are out of C. These two are in C, and the two on the ends are out of D. Oh, sorry, in D and out of D. And so that's it for that one. Next, let's do the red group. So our red group here is entirely inside of A. So we write A. Notice that it is entirely outside of B, right? This is the B range up here. It's outside of B, so we write B naught. Notice that this one is in C, but this one is not in C, so we don't write C. Remember, if it's half in, half out, you don't write it. And both of them are inside of D, so we write D. So that's it for that group. Last one, our white group in the upper left. Notice that it's entirely outside of A. It crosses half in, half out of B. It's entirely outside of C, and it's entirely outside of D. This over here is nowhere near C or D. That's it. That's the simplest that equation can be done. Alright. What about this one? Go away. I thought I had a fix for that. Alright, so again, we want to make the group as big as possible. You should try this one. What's the biggest group you can make here? You see it? Look at this. Oh yeah, this is what I want to see. We're going to simplify the heck out of this guy. Group this with this over here. Look at that. That's a huge group. Alright, what's next? Well, we got 4 sitting right here. And then finally, these two. At least they're a couple, right? They're not totally alone. Boom. Label our regions. A. B. The regions never change, by the way, so you can just memorize them, but you don't really need to memorize it. It's pretty easy to find out where they are just by looking at the letters on the sides. I mean, the numbers on the sides. Alright, blue group first. Notice in A, out of A, don't write anything about A. In B, out of B, don't write anything about B. This over here is in C, out of C, don't write anything about C. D, notice all of it is outside of D. It hates D, it doesn't want to be anywhere near D. We write D naught. Next up, the red group. Half in, down here's in A, outside of A, don't write anything. All of it, though, is inside of B. All of it is outside of C, and it's half in, half out of D, so we don't write anything else. Next up, the white group. All of it is inside of A. All of it is outside of B. All of it is inside of C, and it's half in and half out of D. Done. Told you it wasn't that bad. Those rules make it look scary, but it's not that bad. Oh, look at this. Now we're for the challenging ones. So we've been given a circuit. We need to know how can we simplify this, right? Our boss says, hey, we need to build this, but we want you to check it out to make sure we're not wasting company time and money. So, how do we simplify this? Well, we're going all the way back to the beginning. Step 1, De Morgan. De Morgan. Alright, so this is one of the tricky ones we have to De Morgan. Remember, I see it over a few things. I see it over this, then over this, then over this, then over this, then over this whole thing. I'm not going to skip steps. So I've got A, not, this OR becomes an AND. C, not, this OR becomes an AND. And then I've got it over B, C, not. You're going to see why in just a second it's important I don't skip steps. Alright, the double not cancels for A, the double not cancels for C, even though I just wrote it for some reason. And notice we now need to basically, we have that last OR bar over this, and this. But remember, if you're ever going to a situation where something's going to switch to an OR and it's currently a part of an AND, parentheses. So that's going to leave me with B naught or C not. And finally, we're going to be left with AC, B naught, or C. This still is not good enough, though. Remember, we need to have it in sum of products form. And so I need to multiply everything out. And so that's going to give me A, B naught, C, or A, C, C. Not a very good college football conference. Somebody's going to get that in the class, maybe. Okay, so what do we got to do? Well, remember, we don't need two C's. And move this over, I should erase that one. So, are we done? No, not yet. Not in standard form. Turns out we're missing a B there. And so, this will be true at 1, 0, 1. At 1 and 1 for A and C, but B could be 0 or 1. So, now we need to fill out our K-map. So, at 1, 0, 1, that's here. And at 1, 1, 1, that's there. Put on our regions. A, B, and C. Looks like this one's pretty simple to group. Write out our equation. It's entirely inside of A. It crosses B. And it's entirely inside of C. And that seems to be it. And so what that means, instead of building this hot mess up here, your company really could have just done A, C, stuck an AND gate there and called it a day. This is why K-mapping is so important. This is way easier than doing the Boolean substitution stuff we did before. And notice, we go from 1, 2, 3, 4 inverters, one AND gate, and an OR gate that has 3 inputs, down to just one AND gate. And even better, B isn't needed at all. In real life, this A, B, and C stuff, those are inputs. That was probably some $50 sensor that your project doesn't even need. This is why K-map is so powerful. Alright, now we don't care. What? I gotta teach you one last thing. This is a technical term. Don't care conditions. So, for lots of designs, I can't really give you a good example now. I can kind of try to give you an example. We're gonna see a lot of them later on. There are certain outputs we literally just don't care about. Like, later in the semester, we're going to work with something called a 7-segment display. Looks like this. It's kind of, if we were in the lab, I'd show you all the equipment has them on there. Or if you look at older displays, where, you know, if you want to put the number 2 out, you just turn this one on. Like that, and you get the number 2. Well, in those displays, values over 9, so 10 through 15, they just can't happen. Right? They just don't happen. They can happen, whatever. And there's lots of different systems that we build where, because we're forced to have powers of 2, we may only need the first 10 values. And so what a don't care condition is it means we don't care what the output is. Just to make it more interesting, I also said I don't care about what this output is. So when we don't care what the output is, let me show you how we build this. Instead of putting a 1, if it's a don't care, we put an X. So at 0, 0, 0, I have an X. Just like before, we don't write zeros ever. At 0, 0, 0, it's 0, 1, 1, 1. So 0, 1, 1, 1, I have a 1. At 1, 0, 0, 0, I have a 1. At 1, 0, 0, 1, I have a 1. Now, just to show you why this is so useful, let's say that we didn't use don't cares. Let's say that I just made them all 0, right? Because that's what we could do. That's the alternative, is I could just make them 0. Well, if I were to do this right here, right? So let me just pull it over for a second. We would have 2 groups, right? I would have a group here, and I would have a group here. And so our first group, the blue group at the bottom, would be inside of A, outside of B, outside of C, and crosses D. So that would be the blue group, and the red group would be outside of A, inside of B, inside of C, and inside of D. So that would be our equation. But if we really don't care what the value is, we can do better. Because right now we're forcing it to be 0. We're saying it has to be 0. Instead, if I say that, what do we got here? 1, 0, 1, 0. That's here. I don't care. 1, 0, 1, 1. Don't care. 1, 0, 1, 1, 0, 0. Don't care. 1, 1, 0, 1. I know it's harsh, but I don't care. 1, 1, 1, 0. Don't care. All ones, don't care about you either. Now the way that don't cares work is we use them in a group if it helps, but if it doesn't, we just ignore them. So like these two down here, instead of making a group of 2, I'm going to make that a group of 8. Because I don't care. This one here, I'm going to make that a group of 2. Boom. Because it helps. See this one up here? I'm going to ignore it. It doesn't help. I just ignore it. Let it be 0. And now we can do our groupings. So now notice, for this group here, it's entirely inside of A, but it crosses B, it crosses C, and it crosses D. Done. The red group? Well, it crosses A, it's inside of B, inside of C, and inside of D. And so notice, this is a better circuit than this. And so that's how you use don't cares. Basically, you use them in a group if it helps you to. If it doesn't help you, you just ignore it and don't use it at all. And I think that's it. For the second time, I have finished this lecture. I hope it's sort of easy. I hope it makes sense. It's really powerful. Please review it. We have our first test. We're not going to have any more lectures before our first test. Because we've covered a lot of material and it's so important, I have a week of review for you. But if you have questions, let me know. Otherwise, practice, practice, practice. Do your homework. Don't wait a week. You're going to forget it all. Talk to you again later.